Alrighty, it's a hot day today, so you might be hearing the air conditioner going on in the background. It's a little portable thing, but um, we can just continue. All right. So where are we at? Chapter 4. Separating files. So here we go. If you have common features, chances are when you begin to write several programs in C, you will find that there are some functions and features that you will want to reuse from other programs. For example, look at the specs of the two programs on the right. So I think we're talking about this one right here. There's a file hider where we read the contents of a file and create an encrypted version using XOR encryption. And then there's a message hider. We read a series of strings from the standard input and display an encrypted version on the standard output using XOR encryption. So XOR encryption is a common thing here. XOR encryption is a very simple way of disguising a piece of text by XORing each character with some value. It's not very secure, but it's very easy to do. And the same code that can encrypt text can also be used to decrypt it. So here's the code to encrypt some text. So we have this encrypt function that takes in a pointer to a character, so that's going to be like a string, most likely. Then we declare a character C, and we're going to have a while loop that will, as long as there's some sort of valid memory address, meaning that we don't hit the null terminating character, because null terminating character is actually, well, sorry, I need to read this while loop correctly. We're going to dereference the character at that memory address, and so when we dereference the character at that memory address, if it's a null terminating character, that's a zero value. So that's a falsy value, right? So this is dereferencing the character at the current memory location. And then yeah, so if there's a character, it'll execute the loop body. And if we have a null terminating character that got dereferenced here because of the asterisk, then that's a falsy value, and then we exit out of the while loop. So inside the body here, we're just dereferencing the character at the current memory location pointed by this pointer here, XORing that with 31, and updating. Notice this dereference up here, right? This asterisk. We're going to update then. Update the value into this memory location, and then we're going to here's a pointer form, right? Pointer. We're going to increment the memory address by the size of the character, which is 1. Characters are 1 byte, so 1 memory address. Whew, that's a lot just for a simple loop. Um, so it's good to share code. Clearly, both of those programs are going to need to use the same encrypt function. So yeah, these two programs would want to use this common XOR thing here. So remember, this is like the XOR encryption utility function. So you could just copy the code from one program to the other, right? That's not so bad if there's just a small amount of code to copy. But what if there's a really large amount of code? Or what if the way the encrypt function works needs to change in the future? Then you'll end up changing you'll end up changing one program, and you have to change the other program because you kind of copied and pasted. Um, if there are two copies of the encrypt function, you will have to change it in more than one place. For your code to scale properly, you really need to find some way to reuse common pieces of code. Some way of taking a set of functions and making them available in a bunch of different programs. So how would we do that? You can split the code into separate files. If you have a set of code that you want to share among several files, it makes a lot of sense to put the shared code into a separate .c file. If the compiler can somehow include the shared code when it's compiling the program, you can use the same code in multiple applications at once. Okay, so reuse, right? Just use that common.c file. So if you ever need to change the shared code, you only have to do it in one place. Okay, so here's the shared code. Here's like the encrypt file. So this is the first program. This is the second program. Basically, they'll just import. They'll import this encrypt file, and they'll use the functions available in that file to do stuff. If you want to use a separate .c file for the shared code, that gives us a problem. So far, that gives us a problem. Let me read that again. If you want to use a separate .c file for the shared code, that gives us a problem. There we go. So far, you have only created programs from one single .c source file. So every time it's always main.c, main.c, main.c. We never went beyond that. We've jammed everything in to one file. Okay, so if you had a C program called Blitz Hack, you would have created it from a single source code file, maybe called blitz_hack.c. But now you want some way to give the compiler a set of source code files and say, go make a program from those. How do you do that? What syntax do you use with the GCC compiler? That's a good question because we've only been compiling one file. So now we're needing multiple files. How do we actually do that? How do we take into consideration of that second file that we're including, right? So in C, including is like importing. What does it mean for the compiler to create a single executable program from several files? How would it work? How would it stitch them together? To understand how the C compiler can create a single program from multiple files, let's take a look at how compilation works. Okay, this is going to be good. So this is like the whole compilation process. So compilation behind the scenes. To understand how a compiler can compile several source files into a single program, you'll need to pull back the curtain and see how compilation really works. So we do pre-processing. Fix the source. Hold on. Okay. Let's see. Yeah. Pre-processing. Fix the source. So remember I mentioned something about like these are like kind of like macros and they're not really part of the C language. The compiler or at least the compilation process like does special things with these types of lines with the pound. There's like a bunch of replacement and things like that. So that's what pre-processing is. The first thing the compiler needs to do is fix the source. It needs to add in any extra header files it's been told about using the pound include directive. It might also need to expand or skip over some sections of the program. Once it's done, the source code will be ready for the actual compilation. So the computer's like, so I need to compile the source files into a program? Let's see what I can cook up. First, I'll just add some extra ingredients into the source. So these are like the header files that you include, or the .c files. And that's the preprocessor step. Then the next step is to compile, translate into assembly. The C programming language probably seems pretty low level, but the truth is it's not low level enough for the computer to understand. Ouch. The computer only really understands very low-level machine code instructions, and the first step to generate machine code is to convert the C source code into assembly language symbols like this. Move Q negative 24. I don't know all this stuff. I'm assuming that's like x86, so it's assembly code here. So for this if statement, I need to begin by adding onto the stack. Okay, looks pretty obscure. Or no, looks pretty obscure? Yeah, there we go. Assembly language describes the individual instructions the central processor will have to follow when running the program. The C compiler has a whole set of recipes for each of the different parts of the C language. The recipes will tell the compiler how to convert an if statement or a function call into a sequence of assembly language instructions. So it's kind of like a mapping, right? But even assembly isn't low level enough for the computer. Wow. Whoa. Whoa. That's why it needs, whoa, to generate the object code. Nice. The compiler will need to assemble the symbol codes into machine or object code. This is the actual binary code that will be executed by the circuits inside the CPU. So these are just translating to numbers that the computer kind of understands to do stuff with it. So like, some codes will tell it to add, some codes will tell it to subtract, and then like these codes are like pre-programmed saying, hey, if you have a code that's adding, the next couple bytes, right, are like the operands. And so like it's a special sequence that has to be done, and like special values inserted for the CPU to understand what to do. So are you all done? After all, you've taken the original C source code and converted it into ones and zeros that the computer's circuits need. But no, there's still one more step. If you give the computer several files to compile for a program, the compiler will generate a piece of object code for each source file. Okay, let's read that again. If you give the computer several files, so many C and header files to compile, the compiler will generate one piece of object code for each of those source files. But so then you'll have multiple object files, and I think these are the .o files that we normally see. In some, sometimes when we like download programs, we'll see like .o and things like that. So in order for these separate object files to form one single executable, so we want to be able to take all of these object files, these .o files, and put them into one, like, for example, what we see a.out file, this executable. There's one more thing that has to occur. We have to link. So we had to put it all together. Once you have all of the separate pieces of object code, you need to fit them together like jigsaw puzzles to form the executable program. The compiler will connect the code in one piece of object code that calls a function in another piece of object code. The compiler will start to connect the code in one piece of object code that calls a function in another piece of object code. So then that's how it makes sure that they're like dependent on each other, okay? And the linking part will also make sure that the program is able to call the library code properly. So linking is that process to do that connection. Okay. Finally, the program will be written out into a single executable file using a format that is supported by the operating system. The file format is important because it will allow the operating system to load the program into memory and make it run. So think of that single executable as like the combination, like the bundle of all those object files, where every object file is now aware of each other. In this case, because they're all like linked. Like if one function calls another function from one file to the other, like that part is linked, and then now the operating, or not the operating system, the linker will bundle it all together into a single executable. I'm just regurgitating what the book's saying. Okay. So how do you actually tell GCC that we want to make one executable program from several separate source files? The shared code needs its own header file. So header file, what is a header file? These are like the .h files that we see here, right? was it main.h? Remember how we had this the declaration of the function? Okay, so if you're going to share the encrypt.c code between programs, you will need some way to tell those programs about the encrypt code. You do that with a header file. Yeah, let's start writing code. Let's create a project that mirrors this. So I'll have encrypt underscore XOR or hyphen encrypt hyphen XOR for this. Then we'll have what is it? Looks like encrypt.h and encrypt.c. Then an encrypt.c. Okay, so let's sort. Encrypt.h should be pretty easy. So it's just void encrypt character pointer message. Save that. And then we'll have encrypt.c. So that's easy. We'll just include encrypt.h. And then we'll have void encrypt character pointer message. So same signature, right? Same signature as the encrypt.h. We're just providing the implementation now. So the definition of our function. So we'll do character C, and then we'll do while dereference the value pointed by message. We're going to update the value stored in message at that specific memory location with the value that is evaluated from dereferencing the current character pointed or the value pointed by the message pointer and XORing that by 31. And then we'll also increment the address pointed by message by 1. So that's pretty much it. So we're modifying the message in place. We're not, notice how we're not returning anything. We're like modifying it in place. Okay? So we include the encrypt.h, sure. And then we have to create now, so this is like our library. This is like our reusable code, right? So now we have to create a new program that uses it by including encrypt.h. So let's read this. You're not using a header file here to be able to reorder the functions. You're using it to tell the other programs about the encrypt function. So yeah, so like just to remember here, this is just to let us or let the compiler know that we're declaring this encrypt function right before we use it. Remember when we use functions, they just need to be declared because during the rest of the compilation step, the real definition will eventually be like picked up and I guess like associated with that function call anyway. But in that moment where the compiler is trying to understand like what the return types are of this function, what the arguments like required, like parameters, right, for your arguments, that like a declaration is enough, and that's why we would just need to include the header file. So from the previous session we discovered. So we can create then yeah, a new program called messagehider.c here. And then we can just say include, oops. Okay. Then we're going to also include the encrypt.h. Okay. Main. Then we'll declare a buffer of 80 characters. Then we're just gonna get fgetS the message, like data received from like the user into the message. And then after that, as we're receiving the input, we want to just encrypt it in place. and then we're going to print out the encrypted version of the message. So this gets one line at a time, right? 80 characters, one line at a time, encrypt it, then print out the encrypted version. And going back here, notice how encrypt C also includes encrypt.h because we need to provide the implementation of this function that was declared. And since we're importing encrypt.h, instead we're going to get the declaration, but the implementation of this will be, since it's all connected through this header, we'll actually get it from here. Right? So by simply including this header file here in this C file, it actually makes the compiler like aware that this would be the definition for the function inside here. Because when we pre-process, what's really happening is that this is actually replaced like this, right? So, yeah, okay. But yeah, generally that is like the pattern from what I'm understanding here. Okay, so now we have these three files. So let's see what's going on here. Having encrypt.h inside the main program will mean the compiler will know enough about the encrypt function to compile the code. At the linking stage, the compiler will be able to connect the call to encrypt message in messagehider.c to the actual encrypt function in encrypt.h. Finally, to compile everything together, we just need to pass the source files to GCC. So now when we're compiling, we have to actually compile every C file, and then we output that to a single program. So we can do that. We had to specify all the C files because now they're dependent amongst each other. So let's see, cd encrypt xor gcc message hider.c, then encrypt.c -o message hider. Oh, I said SCD, it's the SCD in. So let's go back and fix our mistake. Oh, geez, my computer. Okay, STD in. Then, okay. So if we list our directories, we'll see this message hider binary, and we'll just execute that. And then we can say, hello there, how are you today? And we'll get like an encrypted text. Cool. Hello again. What do we see here? All right. Yeah, you see, it's not very secure. Okay. So now, what happens if we delete this file right here? Okay. And what happens if we never included the second C file? We just compiled message hider and did not provide encrypt.c. Okay, so now we get an error, right? What's happening is that we can't figure out where the definition of the encrypt function is from. We had the declaration, but we never found the definition, and that's what the compiler is complaining about. And that's the reason why you need to keep track of every single file that you actually use in your project. Okay? So, yeah, so we got that. All right. So now, yeah, what they're saying is that now whenever we want to change the encrypt implementation or update, we just need to modify one single file. And every program we create using encrypt is not going to need like double, triple, whatever modifications. So you'll notice something as like projects get bigger. This guy's complaint is real. Man, every time I make a simple change in one file, it takes an age to recompile, and I'm working on a schedule. Yeah, so that's the thing. It's like if you change this encrypt file, you need to recompile a program. You have to specify all of this again. Okay, all the files again. That's kind of inconvenient, right? But I think there's a solution. So let's see. So it's not rocket science, or is it? So breaking your program out into separate source files not only means that you can share code between different programs, but it also means you can start to really create large programs. Why? Well, because you can start to break your program down into smaller self-contained pieces of code. Rather than being forced to have one huge source file, you can have lots of simpler files that are easier to understand, maintain, and test. So on the plus side, you can start to create large programs. The downside, the downside is you can create really large programs. C compilers are really efficient pieces of software. They take your software through some very complex transformations. They can modify your source, link hundreds of files together without blowing your memory, and even optimize the code you wrote along the way. And even though they do all that, they still manage to run quickly. But if you create programs that use more than a few files, the time it takes to compile the code starts to become more important. Let's say it takes a minute to compile a large project. That might not sound like a lot of time, but it's more than long enough to break your train of thought. If you try out a change in a single line of code, you want to see the result of that change as quickly as possible. If you had to wait a full minute to see the results of every change, well, that will really start to slow you down. So, how do we fix that? The solution: just don't recompile every file. If you made a change to one or two of your source code files, it's a waste to recompile every source file for your program. Think what happens when you issue a command like this: blah 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 dot 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 engine.c dash launch. What will the compiler do? It will run the preprocessor, compiler, and assembler for every single source file, even the ones that haven't changed. And if the source code hasn't changed, the object code that's generated for that file won't change either. So if the compiler is generating the object code for every file every time, what do you need to do? Save copies of the compiled code. If you tell the compiler to save the object code it generates into a file, it shouldn't need to recreate it unless the source code changes. If a file does not change, or a file does change, you can recreate the object code for that one file and pass the whole set of object files to the compiler so they can be linked. So yeah, again, important thing to remember is that when you compile object files, they're like very independent, right? It's not until you start to link where it becomes dependent with one another. So if you actually just change one file, you just need to be able to compile the object code for that specific file. And then the linking process is actually going to stitch everything together. So it's not going to affect like the program itself if you just compile one file to an object file. So it's very modular in that way because that stitching and that dependency stuff doesn't happen until the linking process. At least that's how I'm reading it. Okay, so okay, yes, yeah. So here, see, it's like C source files, compile, object files. Then you link them into executable. So if you change a single file, you have to recreate the object code file from it, but you won't need to create the object code for any other file. Then you can pass all the object code files to the linker and create a new version of the program. So how do you tell GCC to save the object code in a file? Yeah, how do we do that? Because we're always like, every time we call GCC, we always get the executable, right? So how do we, instead of getting the executable directly, how about we try to just compile the source code files to individual object code files first? So here's how we do that. And also, how do we actually link those object files manually? So let's learn. First, compile the source into object files. You want object code for each of the source files, and you can do that by typing gcc-c star.c. So the operating system will place it. Okay, we know that. GCC-C will compile the code but won't link it. Okay, so we'll get back object files if we do the -C. So let's try that. It's rm message hider. Let's do GCC-C. What is it? Message hider.c and then encrypt.c. Okay. WLS. Notice that we have our object files right there. Nice. And then we link them together. Now that we have a set of object files, you can link them together with a simple compile command. But instead of giving the compiler the names of the C source files, you tell it the names of the object files with a -O, okay? So we specify the object files individually with a -O option and then the name of the executable. So the compiler is smart enough to recognize the files as object files rather than the source files. So it will skip most of the compilation steps and just link them together into an executable program called launch. Okay, so let's do that. So gcc-o message hider.o encrypt.o. Oh, where's this .o -o after all this? -o, and let's just do message hider as before. Oh, there we go. Yeah, look, we linked it. Okay. Okay, sure. So then if we run it, we should be okay. We should be okay. Nice. Still works. Cool. Okay, so I'm gonna skip this. Looks like it's a long exercise. I think it's just asking you like if you were to I encourage people to do this, but it's like what would you need to change, like if you were to change a file, what do you need to recompile and what changes during the linking process? So anyway, it's hard to keep track of the files. I thought the whole point of saving time was so I didn't have to get distracted. Now that the compile time is faster, but I had to think a lot harder about how to compile my code. Where's the sense in that? So like in a way you save time, right? But you save time by having to keep track of all these files, and that's like pretty painful. So yeah, it's true. Partial compiles are faster, but you have to think more carefully to make sure you compile everything you need. If you are working on just one source file, things will be pretty simple. But if you changed a few files, it's pretty easy to forget to recompile some of them. Okay. That means the newly compiled program will pick up all the changes you made. Now, of course, when you come to ship the final program, you can always make sure you can do a full recompile of every file, but you don't want to do that while you're still developing the code. So even though like this is all mechanical process, you know, we can actually script it and automate it. So yeah, wouldn't it be dreamy if there was a tool that could just do this? Yes, it's called Make, and we will discuss that one tomorrow. Okay, let's commit. Okay, cool. All right, talk to you guys later.